Hello, my name is Evan Burke, and this is my VChat fuzzing analysis database project. This project demonstrates an end-to-end system that fuzzes an intentionally vulnerable network service, VChat, detects program crashes, extracts the inputs, and organizes everything into a clean, normalized relational database. The final database is going to allow me to analyze the fuzzing results, compare different fuzzing campaigns, and understand which inputs or commands could be the most risky. So to start off here, we're going to run our vulnerable chat server and do an example fuzzing run against it. So we're going to pop over here to our Windows virtual machine, and we will start up a vChat server. All good. And then over here on my Kali machine, I'm going to clone this repository so that I can make use of the fuzzer that I already have. And this will just take a moment. Anywho, so over here, this is the vulnerable vChat server. It exposes commands like trun, gtr, lter, help, and specifically contains buffer overflow vulnerabilities, slightly different per each command. So this is going to be our realistic target for us to analyze. All right, so we're going to change into our directory here. And as we can see here, we have all of our different fuzzing scripts. We have one for each command here that in the end, I used all four of these to append to each other into a larger database. So we can look at the comparisons between the commands and not just one database for each command. So anywho, for the first example, we will make use of the trun command. So we will run this script. Oh, my apologies. I forgot. I needed to make a CSV directory before I could run the script in order to host. All right, all good now. So we're running our bootfuzz fuzzer here. It generates mutated inputs and sends them into our vChat. Each test case is logged with a mutation name, the number of bytes being sent, and any abnormal behavior being sent or detected. When the target becomes unstable, my custom health monitor will detect a connection reset or unexpected response that's going to indicate the crash. All right, here we can see a crash event. The server connection restarts immediately after our large mutation was sent, which is flagged. At this point, the vChat has crashed. It is unresponsive. The fuzzer is going to report the failure and log it. And what gets logged here are these large artifacts that includes steps, the payloads, and the crash logs. So we can take a look at one of those here. Bootfuzz results. So here we're going to have this large unformatted database. It's going to be a raw SQLite file. And this this database is extremely large for what we need. It contains a lot of fluff and a lot of low-level steps that aren't needed in analysis, as well as the format that it's stored in makes it harder to perform analysis on. So that is the purpose of why I wrote the ingestion script, to make it a lot easier to understand the data that we get from this. So before I do that, I like to rename this file to something more clean for the human eye. And then from there, we want to run our ingestion script. And before we can do that, we need to change our ingestion script to know that it's targeting the trun database and the trun CSV file, because each time you do this and you run the fuzzer for a certain command, you're going to need to make sure you specify for the ingestion script which database to actually look at. Because, for example, we could have our raw unfiltered Trun database, GTR database, and we want to make sure that we are ingesting the correct one. So we will go into the ingestion script here. And right here we can see we have the old database, which is going to be that database that was just created by a fuzzer. We're going to change that, the name that we just gave it, which was Trun. And down here, oops. And down here, we want to change this to Trun for the CSV file that was also generated from the fuzzer. And up here, change this to Trun. We will save that. We will back out. And we will run our ingestion script. And boom, as we can see here, we have a nice command line information here that we're going to see that our ingestion is complete and one crash was recorded, which is the expected behavior from that. Assume from what we saw that there was only one crash when we were running the fuzzing against the VChat server. So the ingestion script is going to load the original BooFuzz database. It extracts each test case metadata, detects crashes based on monitor failures, and retrieves the crash causing payload either from BooFuzz's step table or from the fuzz log, which is our CSV file. More often than from not, it grabs it from the CSV file. The injection script then inserts everything into our own analysis database using a clean schema. And importantly noted, the system supports multiple fuzzing runs. So if we were to do this again, run the ingestion script for instead of Trun GTR, it's going to append the data to that existing database that we have as opposed to making an entirely separate one. So now let's take a look at our database schema. Here we are. So this database was designed using third nominal form, meaning each table represents a single concept. There is no redundant data, and the relationship between entities is modeled by using primary and foreign keys. We have 4 tables in this schema. We have fuzz runs, test cases, crashes, and crash inputs. Together, these tables describe the full life cycle for a fuzzing campaign. So for our fuzzing runs, this is going to be what represents a single fuzzing campaign. So each time I run the fuzzer, whether it's for Trun or GTR or any other command, I'm going to insert one row into fuzz runs. It contains run ID, which is going to be the primary key, start time, which is the start time, total cases, how many mutations the fuzzer is going to be generated, and total crashes. This table lives at the top of the schema because every test case and every crash is going to belong to a specific fuzzing run. Moving on, we have test cases. This table stores every test case generated by BooFuzz, including the mutation name and the case number. So some examples might be, we have Trun, and we're going to have Trun string 35. Each test case is going to have a case ID, which is going to be the primary key. We're going to have the run ID, which is going to be the foreign key to fuzz runs. We have the case number, which is the mutation index, the case name, which is the mutation pattern BooFuzz used, and timestamp. This table models all inputs sent to the target, not just the ones that crashed. So we have all of that data about things that were sent that didn't cause crashes, as well as what might have caused the crash. Moving on to table 3, we have crashes. This represents the events where the target program failed. A crash belongs to exactly one test case and exactly one fuzz run. So we have these columns here where we have the crash ID, which is the primary key. We have the case ID, which is the foreign key to test cases. We have the run ID, the timestamp, and the crash reason, which could be something such as the connection reset or monitor failure. This lets me trace every crash back to the exact mutation that caused it. Moving on, we have crash inputs. This includes both text-based strings and raw binary blobs, depending on what the fuzzer generated. Each crash has exactly one payload, making this a one-to-one relationship. Columns include input ID. We have crash ID, which is the foreign key, payload, and we have the payload size. This table is crucial because it preserves the exact bytes that broke the target program, which is the most important thing for fuzzing because we want to know what actually caused the program to crash. In a real-world security context, these payloads are what you would use to exploit development or to reproduce or crash or to show the vulnerability in the program. So overall, the schema provides a clear and normalized representation of fuzzing data. Every fuzz run contains test cases. Some test cases produce crashes, and each crash is associated with the exact payload that triggered it. This design makes analysis easy, scalable, and scientifically accurate. So now I'm going to move on to demonstrating some SQL queries that we can use given a fully built out database. So like we had here in the beginning, we have our Gmon fuzzing, we have our GTR fuzzing, we have our help fuzzing, and we have our trun fuzzing. It would take some time for me to run all of these and then ingest them into the main database. So I have that database already ready to look at. So that is what we will do here. So here we have a SQL query that's going to find us all of said commands that ended up resulting in a crash. So if we run this, we're going to see that we have commands gter, trun, and gmon, as well as their associated run IDs, the crash reason, and crash time for all three of these. And so you're going to notice that there's a lack of one command here, and that's because it did not result in a crash. Moving on, we're going to find all of the commands in our database that did not result into a crash. So we want to know what commands we were not able to cause a crash through. And right here, we can see that this is run ID 4. Do we know what run ID 4 is right now? No, we don't. But if we take a look at our database structure, we can see here the run ID associated with each case name. So just by taking a look down here, if we go down to 4, we can see that this is for the help command. So knowing that, we know that the help command the help command was immune to our fuzzing, at least for the time period that we ran it. And for our third query here that we want to run, we want to find all of our payloads that caused site crashes. So the exact inputs, including the binary that crashed the program. And right here, you see that we can see the payload that crashed for the trun command in its text form. And then here for Gmon, we have the raw binary data. We can see it decoded over here into what would have been the text form. But nonetheless, this is very important so that we can grab the specific payload and replicate it or try to exploit it, determining what aspect of the payload, whether it be the size or the exact data that was sent in it, caused the crash. And say that we wanted to find the crash data for a specific commands like trun or gter or gmon. We can do that here. So say we wanted to find the specific crash payload for trun. We could run a query like this. And right here, we have that information. And we have our payload that caused the crash for the trun command. Let's see if we can do this for gmon. Boom. We can see the one that caused the crash for gmon. I think this one is one of the more useful SQL queries that we can do. But yeah, anyhow, as you can see, there's a general understanding on finding what payloads caused said crashes, what commands were vulnerable to crashes from fuzzing, which ones weren't, and what the said payloads were, I think is the most important data to grab from fuzzing. So to wrap everything up, this was a full crash analysis system that integrates fuzzing, crash detection, ingestion, relational database design, and analytical SQL queries. This project demonstrates concepts from cybersecurity to software testing and database systems all working together to uncover vulnerabilities in an unsafe program. Thank you.